Well, hey everybody, welcome back. We are doing Calc 1 product and chain rule today, two of the most important things you'll probably ever do in Calc. And I got a little bit of cough today, so I'm going to be muting my mic often so you're not having to listen to me cough. But I do got some coffee here, so hopefully that'll be okay and my voice won't give out. These are not easy topics, product and chain rule, if you haven't really learned about them before. So this is not to teach you guys the product and chain rule. This is more of a review. And it's, again, more for my edification and just my going back and relearning some of this stuff and kind of seeing if I can regurgitate it like I used to be able to do. And if people want to listen, great. If they want to join in, even better. But again, I'm just kind of doing this for myself. Don't take me as a math person. I'm not a mathematician. Not by any stretch of imagination. So what I'm saying is not gospel, but we'll see if we can get through this. Anyways, I got Midnight in here, and I got Barney. He's a stream whore and just drops into any stream we have. So now he's going to learn. He's going to learn.
Hey.
Oh, but this coffee's so good. And you got coffee too, right, Barney? You good to go?
Yeah.
Midnight, did you get some coffee?
I before, not now, but yeah.
Okay.
Let's do this.
Yeah, we're gonna jump on into this. I am gonna be pretty much taking this right out of Wiki for the most part, with my own things added in from college textbooks and other things. And one of the things for the Wiki, when you go to it and you look up something like the product rule, it does a very simple proof and does a more rigorous proof. But of course, it's not going to explain to you how these proofs are done. And so it's one of those things. Again, you can go to Wiki; it's great for getting resourced information, but it's not going to teach you anything. It's not going to tell you how these things actually work. So I'm going to be kind of going through how they did their proof and what these things actually do. So what exactly does the product rule do for us? So let's jump right into this and go screen share. Watching so they can't tell me in the outside chat.
Wait, hold on. I can check. I've looked. I haven't. Okay, it still needs to catch up.
I'm pretty much talking to myself, which is okay. I'm used to that.
There we go.
Yeah.
All right, so can you see this?
Yes.
Yeah.
Okay, so what the
outside
product
check
rule
doesn't
allows
see it.
what the product rule allows us to do is remember the composite functions we talked about yesterday, F and G are functions. If they are differentiable functions, so the product of the functions are being able to be differentiated. So if each individual function can be differentiated, then the product, meaning the multiplication of them, can be differentiated. The way you do this, though, is a very specific way. You just don't take both functions and multiply them together and get something out of it. It's not like a composite function where you take one function and you stick into another. The way it actually works out is given by this very specific formula. And what this formula is function f of g, or excuse me, f and g, derivative of that is equal to the derivative of the f function times g plus the f function times the derivative of the g function. Now, there's different ways to write this. Here's where the confusion comes in calculus. This has already been the issue that I had. Depending on what book that you read, depending on what video you watch, depending on what school you go to, you can have different notation for the same thing. This is the primary formula. The way I like this formula only for the fact that I can just set it up and go FG, 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 right? And then I just put in, okay, the first one is just going to be parentheses, this little apostrophe, right, looking thing. That means prime or derivative. So I just have, okay, the first term is going to be the derivative of the first function times the second function plus the first function times the derivative of the second function. So I just set it up FG, 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 and then I just put the little primes in. The other ways of doing it are writing it like this. You could write it in terms of a third function.
Form.
Yeah, this is a third function. So this is h prime of x is equal to this right here. And then I'm just expressing it in the form of an expanded function with the argument shown, which is x, right? Mean the same exact thing. Another way would be with the dot product, or excuse me, God dang it. It's not a dot product, it's a multiplication symbol. But in vector, this means a dot product. So that's why it's a dot product. But this is again, the same thing as this. This is just called implicit multiplication, or you might have heard it as implicit multiplication by juxtaposition. This is explicit multiplication, same thing. Then we go into the more verbose ways of writing things. This is Leibniz notation, and this is d over dx of u or v equals u dv with respect to x plus v du with respect to x here. So this is a very common way of writing it, and I like this particular way of writing it because it actually shows you what you're taking the derivative of, and it helps in differentials. But the prime notation here is more. What's that?
Do you like the d over dx, or do you like f of a f prime? I couldn't really see.
I like the d over dx, but it doesn't really matter because you can switch back and forth, and there's different reasons to use different ones, I think, right? Some notations are easier to use for certain things, and then for longer works, compact notation. And actually, you know what? I even forgot a notation here. I was trying to come up with different notations that I could think of. And when I'm done, there's one more notation that I forgot. We'll see if anybody can note it. But this one's next one called the D notation. This is just saying D, the derivative of y with respect to x, is equal to the derivative of y with respect to u times or multiplied by the derivative of, actually, you know what? No, that shouldn't be times. There should be plus in there, shouldn't it? Yeah, that has to be plus. Okay, so the derivative of u with respect to x. And then the next notation is differentials, right? This little dv here, or du, those you'll see a lot in differentials when you're doing the differential, diffie-q differential equations. When you just say what a differential is used for is, let's say you have a ball bearing, and I want to know how much of that ball bearing is left after it's being worn down, right? Well, one of the ways I can do that is I can take a micrometer and I can measure across the ball bearing and across the x-axis. I can take a measurement across the y-axis, and then I can take an average of that, and that'll give me an average of what my somewhat average of the diameter of the ball bearing. I could then use the formula for volume, and I can take the derivative of that, and I can stick in the error measurement of my micrometer, because usually about 0.0 is it 0.01 or 0.001 millimeter, I think, is the error measurement for micrometer. It's either 0.01 or 0.001. I honestly don't remember, but that error measurement has to be factored in, because when you're taking an error measure, when you're just taking a two-dimensional measurement across the diameter, right? Even in two planes, x and y, when I take the volume and to find out the whole volume of the thing, I have to factor in that micrometer's error measurement, because if I say it's 5 millimeter, well, it could actually be 5.01 millimeter, or it could be 0.499 millimeter, right? If with a 0.01 millimeter difference, it has a variance in there, so it could be anywhere in the range from 0.499 to 0.501. And when I put that into the formula for my volume, that's going to actually be a big amount. That's called an error measurement propagation, right? So that's when you use differentials, which we will get into at some point. I probably should have a Bade Uology actually do differentials, because he's probably got it closer in his mind than I do. So let's see here. Somebody on the live stage said, "Aren't you preaching this math to the choir?" Yeah, this is all review stuff for most people, Madness. This is not meant to be a first experience, first thing to a person where they have never experienced math before. However, it does get them exposed that if they do later on get into math, they'll at least know what some of these things are. So it gives them kind of a leg up. But it's basically for my edification and the people in here that want to review this stuff. It's just, we can do it. So let's just kind of explain it. And with Clown Car Posse, if you want to look at it, that's great too, right? So here's the other type of notation. This is using UV notation, which is the same thing as this formula, right? It's just sticking it using UV notation and then moving the primes a little bit differently. So don't get too hung up with the notation. Think about it as concepts, because the concept of taking the derivative of the product of the two functions is basically you're taking the derivative of one function times the non-derivative of the second function plus the derivative of the second function times the non-derivative of the first function. So that's kind of what you're doing. How it's written can vary, but I did forget one notation here, and I think I know how to actually write it out here. Jade, what notation did I miss? You think off the top of your head? I don't know how to write it in this thing.
I don't know. I'm looking. I'm having I'm making dinner, so I'm a
Well,
little
I
distracted.
mean,
There we go. Okay, that's how you write it. So it's called Newton notation.
yes, there you go.
Let's see.
So, and then what the way it would work would be u dot, let's see, u dot v plus v dot u. Let's see if I can stick that in there quick. Okay, there we go. See the little dots above there? So if I did it as this notation,
that.
uv.
Yeah.
I'm not sure how to write it out because I never use Newton notation. So we'll kind of do a mixture.
I've never used it. Yeah.
Yeah, you'll very rarely ever find this type of notation. This is what we call Newtonian notation. So I had to figure out how to use a dot on this program here. Yeah, it's just called dot v. So here the dot is over the actual function that we want to take a derivative of. So if you see it something like this, that could mean that it's a derivative. Now dots do stand for other things, so I don't think there's one thing fixed. But in this type of thing, when you see U notation or whatever it is, that's going to be the first derivative. If there's 2 dots, it's second derivative. If there's 3 dots, it's a third derivative.
Yeah. You might want to mention that in mathematics, certain letters are used for certain things. And it can be really helpful if you're looking at something and you don't know what it is. For example, if you see F and G, you know you're dealing with functions always. And if you see U and V, you're usually dealing with some sort of differentiation. And just like when you see X and Y, you're dealing with specific variables. When you see A and B, you're dealing with general variables, as in doing a rule. And there's
actually with A and B, you're probably going to be using those for constants. The lower.
Or for general rules.
Or for general rule expressions of variables and general expressions. Yeah, and that's
you can
exactly
tell
right.
by the context. But you can tell by the context, and that's what you need to look at. Look at which letters are being used and what context they're being used.
That's a great point. Context.
A equals A is a rule, and in that case, A is being used as a general, a general constant. But if you were going to do, x squared plus 2x plus A, clearly that's being used as a constant there.
It's funny, we talk about context.
General variable in the first.
This is one of those things, because people that learn math, people that learn science, no matter what type of science you take, you have to learn math. STEM, you have to learn math. There's just no getting out of that, right? That's one thing about what Jay just said. People that learn math and other STEM fields learn things about context, and I noticed that's why a lot of people that never had any kind of math or sciences or formal education, they really have a hard time understanding concept in different in conversations. I mean, have you noticed that as well? It's kind of ubiquitous among certain people in our community that have never had any experience with this.
And in this, for example, we see our D's and we know what the D means here, but in a different context, a D could be a constant.
Yeah,
constants, usually start with C. And then you'll go to like B and A, but then you may use D, E, F, although E and F have other meanings too. So you have to look at context, but understanding your what letters are used for what and in what context they're in can help you a lot if you run into a problem that you find. I've had that happen in tests. I looked at the test and wondered what in hell they were doing, and then I stopped and looked at the letters. Okay,
and like this big D notation, excuse me. There's also what's called big O notation, and you'll see like an O with some terms coming out of it and stuff like that. If you've never experienced a Taylor series, if you don't have no idea what a Taylor series is, or when you do high math with primes, you will never know what O notation is. You'll look at this and go, what the hell is O doing there? It's not a variable or anything. It's big O, capital O, but it's called O notation. So there are different types of notations that you may not be experienced with, but again, recognize context and then go, okay, how are they using this context? Like big O notation is just used for expressing multiple terms in a Taylor series, so you don't have to write them all out.
Right. When I started studying upper math, one of the things I did was to make a list of what they were used for. And that helped me remember. Like I said, A, B, C, and D can be used for general variables in rules. X, Y, Z for specific variables in in equations. But A, B, C, and D can also be used as constants in equations. So that's how you look at these things.
Yeah, these H, G, and X, like here, H of X. You generally want to reserve things like F, G, and even H sometimes for functions,
Yes.
right?
Yes.
But you also see H in matrix theory, right? You also see some of these things in matrix. So they do mean
Steve,
different things. Yeah.
Steve, how would you use the product rule if you had three functions?
Well, well, we're going to get into the chain rule when we have more than a couple of different functions, and so this you're basically what you would do is you basically would take the product of two first, then then apply to the third. So basically, you just do them in order. But that's a little more advanced. But let's just stick with two functions right now, okay?
Yeah, I just figured I'd ask.
They are a lot of these things are. Well, I hate to use the word, but chainable, I guess would be the best way to put it. Okay, so
well played.
Let's start with this. So I'm just expressing the product of these two functions with another function. Now, if you remember with the composite functions, you took the input of one. You took the output of one, you put it the input of the other. Here, I want the product of the two. And again, you can't just take the product of the two and times them together. I can't just say, okay, if the function is 2 for f of x and the function is 2 for g of x, well, the product between them is 4. No, it doesn't work that way. Okay. So let's actually see what we have to do here. So let's assume that f and g are both differentiatable. And Rita, do you remember what it means to be differentiatable? If I had say a function is differentiatable, what does that kind of mean? What do you think?
They need to have a derivative.
Yeah, it just means I can take derivative across the function. It has no discontinuity. Okay, it has no breaks. If there's a point in the function where it basically goes orthogonal to the x-axis, which means perpendicular, that would be a 0 for the right. I mean, that'd be undefined for the derivative. You can't have an undefined derivative. So these functions are assumed to be differentiatable. If they're not, you can't take the product rule here. Very, very critical. Okay. And look, we got Richard Bushy in the live chat. Yay, Richard! He's learning math. He's getting out of his bubble from theology, and he's learning some math.
Never mind. Sorry, I was just reading the chat.
General should be here. I invited him, but good for you, Richard.
No, he said General better not be here. Anyways, moving on, Steve.
He's possessive of Robert. Robert is love. Robert is life. So,
okay,
all right, so
moving on.
This is where we have fun in the Great Debate community. It's not just about math. Okay, so moving on. Okay, we're going to prove that h is differentiable at x prime of x, blah 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 blah. So basically, that's the product rule, right? So we want to prove that h is differentiatable at any point for x. We want to prove that h of x is differentiatable. Okay, and again, this is going to be the proof taken exactly off of Wikipedia. So if you go to product rule, you're going to see this exact proof, but they don't explain it to you. Now I'm going to show you what this is because I have it right here. This is the proof that we're going to be going over. Okay. Let me blow this up a little bit so you can see it better.
That looks right intimidating, but it's really not. It's just long.
You know what? You're right. It looks intimidating. And remember when I told you? Remember when we first did first principles, right? I told you it's a lot of handwriting out. This is how it was in college for me. We had to write every little thing out, right? I mean, it was just some of these things did it very, very long, very, very quickly. And you could forget terms. You could forget plus signs, minus signs. Yeah. So when I was doing first principles in college, it gets very tedious. And this is why I said I don't like first principles, because you'll never use them, right? You'll never use first principles after a certain point, because this is just an introduction. And after that, you start using, the rules you've already established. But this is what we're going to be going over. But it is kind of intimidating looking, and if you've never seen it before, you probably won't be able to figure it out. And I'm not going to lie. I'm honest with you guys. The third step in here, I actually was so tired the other day. I didn't know how they got to it, even though I knew it worked out. I put it in Wolfram Alpha. I even contacted EO and said, I don't see what they're doing. I woke up today and re-looked at it and said, oh, yeah, okay, I know exactly what's going on. It was just easy today. But the other day, I was so tired, I couldn't figure out what they did. And then I realized, oh, shit, I totally understand what they did. So, yeah, you don't want to do math when you're tired, just FYI. Get some sleep before a test. Richard says, I don't believe in math. I believe in Jesus. Aw, yeah. Jesus wants you to learn math, Richard.
I mean, I know he's joking, but there are people like that, and I had to. Moving on. Sorry.
Yeah. Hey, Renee. Renee's here learning math too. We love Renee. Hey, Renee, I'm not going to make any girl jokes anymore. That's played out, but you're awesome.
Yeah.
Okay, so what we're going to do is we are going to actually use some factors in here that we know for properties. This is again in math one of my weak points, because I really never know what to put in there to make the proof work, to what I have to add into, right? I understand the concepts, but these are what the smart people do. These are what mathematicians do. They go, okay, I can use this and I can actually make the proof. So that's a little more difficult. We're after the fact. We're doing post hoc analysis of the proofs. But do you see this formula here? We need to know that all this equals this. Do you see what I'm doing here, Midnight? Well, see what they did?
Yeah. Where is it? Okay. You're basically using h prime of x equals the limit of x.
Well, no. You're jumping ahead. Right here, f of x, g x plus delta x minus f of x, g plus delta x. I am taking one term and then I'm subtracting the same term. I'm just saying f of x times g times this, right? These terms here, these two terms cancel each other out. They're zero, right? No matter what you put in here, whatever values you put in, it doesn't matter. It's still zero, right? This is basically saying x minus x equals 0. Do you agree?
Yes.
Okay. So we know that's a property, right? That's one of the properties I think that maybe I think Jade will be going over, right? Additive identities and things like that, additive inverse. So the additive inverse here, if I have x and I minus x from it, I get 0. I think we all agree upon that, right?
Yeah. Now, if you were
0.
Now, just to add this in, if you were using the rule notation, I would say a minus a equals 0.
A minus a equals 0.
Right.
Same thing. Yeah. And what Jade mentioned earlier, there are general forms for certain rules, right? And something like a minus a equals 0 is a general form.
Right.
And that should be noted, because it means you can put any value in for a and it holds true.
Right.
Okay. So this is a fudge factor kind of thing. It's not really a fudge factor, but it's a factoring, something we have to know about factoring in order to make this make sense to us. So from the definition of derivative, we went over first principles the other day. Midnight, does this formula look familiar? This h prime of x limit. This looks exactly like I went over in my discussion with first principles, right? Now you guys are understanding how these things build up to each other, right? I mean, if we would have jumped right into this without going over first principles, this would have been super intimidating, and you'd been like, what the hell, right? Would you agree?
Yeah.
Except for Jade, because Jade obviously knows this stuff, but most people in the live chat would be like, I don't get it.
Yeah, and some people in the stream as well.
Yeah, they're doing that now, you know. No, I'm just kidding. Actually, everybody in my live chat here actually knows math, so this is kind of review for them, I think. So,
well, I mean, you know, I've done some of this stuff before, so it's kind of reviewed to me too, but at the same time, it isn't. You know what I mean?
Yeah. And Brian Stevens says vector x minus vector x equal origin. And also, Brian Stevens, if you remember, the dot product of two orthogonal vectors is anybody?
0.
Yes. Oh my God. How do you know that?
I've dabbled in dot products before.
Damn, dude. Yeah, that's pretty good. That's
yeah. I don't mean to brag, but I've done a little bit of everything. It never mind. We're not here to talk about me.
Here's the truth. I have never experienced any of this stuff. I just Google stuff on the fly when anybody talks about it. I have 1 million tabs open, and I just Jade and I were talking about the other day that you know some of these people think we just literally sit on Google and get exposed to this stuff as they talk about it. I'm like, really?
I like what Richard just said. Steve is trying to teach math and mocks people who don't get it.
Well, I mock the CCP. I don't mock people who don't get it. Not at all. Absolutely not, man.
No, I know. I just found it funny.
I mock the people that do not even bother to try, and then they talk about people that do understand this as if they don't understand it, right? They're telling people that have had an education, you guys are idiots, while the people that don't even understand simple math think they know more than PhDs.
Yeah, that's a Dunning-Kruger effect or something similar like it. Or never mind, I'm going off topic.
Yeah.
But
so, anyways, let's move on. So, so we recognize this formula now. So, if you guys remember, back in one of my initial presentations, this first term here, this h quantity x plus delta x is equal to actually y2, right? And then h of x is y1. So it's basically y2 minus y1. It's the difference between 2 points in the y-axis. So all I'm doing here, all they did, this is actually their proof, is that they just substituted in this factoring thing. That's all they did. They said, you know, that y2 minus y1 is equal to 0. So these, and y2 and y1 are the same point. So all they did was they just put this equation in the top instead. Okay, that's all they're doing. And if you remember, right, h is equal to delta x. There's different ways of writing this. So instead of having like h goes to 0 or over h, you can write it as delta x. We went over that before. The same thing, just expressed differently. So here, what they're saying is as the limit of h goes to 0 for this expression or this equation here, or this part of the equation, it goes to negative 0x, which is just 0, right? Negative 0 and positive 0 are 0. There is no real signage to 0. It's an unsigned number, but it can be positive or negative 0, and they mean the same thing. The only time you have signage on 0, Barney might probably know this. Barney,
Steve, would you mind scrolling a little bit so the whole thing is a little bit to the right?
Yeah, gotcha.
Yeah, until everything. Yeah, there you go. Thanks.
Sure, absolutely. So, hey, Barney, do you know when you would actually have sign 0
in programming?
In programming,
yeah, there's a difference between positive 0, negative 0, and undefined 0, right. And there are some differences in limits, if I'm right, depending on which direction you came from it.
Yeah, and that's exactly true. And then, so here's the thing: when you're talking about certain topics, you got to know what your framework is, right? Because if people say in math, a mathematician would say, "Oh, there's no signage for 0," but a programmer would say, "Yes, there is." And especially, correct me if I'm wrong, it's been for a while since I programmed, but a lot of that would be for error management and error captures and error functions and error subroutines.
How can 0 be negative or positive?
It depends on which direction you come from.
Approaching from the left, approaching from the right. Well,
yeah, no, I get that, but where does? Never mind. Moving on. It's
just all you need to know that if you see minus 0, it's literally just saying 0.
Yeah,
okay.
it just.
And technically, I kind of look at like 0 minus 0 is not really saying negative. Excuse me, not saying minus 0. It's actually it's well, it's not really saying negative. It's saying minus 0. It's just saying that you're approaching it from the left-hand side. That's really
okay. It's right. It's just the wording threw me off.
Think of the number line, right?
Yeah, I get. Sorry to interrupt you, Jude. I do get it. Just the way it was framed.
Okay.
Yeah. The important thing is that it's consistent. That all of the rules still apply. If you write down negative 0 and multiply and divide and all of the rules will still apply.
Yep.
Right.
All right. So the next step in their proof is they. Let's see what they do here. Yeah, they just put it in twice. So basically, they're just putting the same quantities multiple times. Okay, and the reason they did this is because we're going to be factoring in a minute. This is the step that I was like, I don't see how they got this. And then I looked at it again this morning. I was like, oh, this is easy. All they did between this step here and this step here is on this side right here, they factored out f of x. Okay.
Oh, so by the way, Steve, did you mean to write g of x? Shouldn't it be x? Like the second line should have x plus delta x, not g plus delta x.
What are you looking at? This should be right out of Wikipedia. I think. I don't know. Well, let's go over it first and see if it works out.
Yeah.
Okay. So we know this right here would cancel out with this right here. So this minus this would cancel out with, this would cancel out with this. Oh, okay, I see what it is. Okay, so look at this middle part. These two terms in the middle, right? Cancel would cancel each other out, right? Because this is a minus here. And then all you're doing is you're sticking in between these two terms. Is that right? Hang on.
I may need to do this proof on my own later.
Yeah, well, hang on. I see what they did. Okay, again, it has to do with factoring. This is again. I'm trying to visual in my head. I didn't do the steps. If you normally do the steps in a proof, you'll see how things are done. But since I copied this one, I had to see how they did it.
Yeah.
Again, what they did was, see this f of x right here that I'm pointing to.
Uh.
Can you see my pointer?
Yes.
Okay.
No.
This f of x. You guys don't see my pointer? Some people do. Some people don't.
Can I? Yeah. Can I
It's dead set on my screen.
suggest? Can I suggest in the future you get a larger pointer?
I don't know how to do that, to be honest with you.
Oh, okay. Well, you can. Guess what? You can Google it.
Yeah, Google it. Yeah, you know, it's fun. Yeah, Google. So it takes time to do that, right? It'll take me 5 minutes to figure that out. But
Yeah,
anyways, I am gonna try to get a little writer. I think I found one that might work, and I'm gonna put it on my wish list. And I think somebody that has offered to maybe pick it up for me. So I'm gonna be able to do this in a different style as well. I think it'll be. You guys don't see the pointer.
Steve Academy.
Steve Academy. So, you know, if you don't have the pointer, let me see. I might have a better way of doing this. So let me see here. What can I use here? What's a good symbol to use to where my pointer is for people? Oh, let's type here. Here we go. Here we go. Here. Here we go. Okay, so here is what I'm talking about. So the live feed, what I'm talking about here. This f of x right here after here is just being factored out from these two things here. I'm taking the f of x from here, and I'm taking the f of x from the f of x of g of x, leaving me just f of x with gx plus delta x minus g x, right? It's all I did was factoring it out, and then I put in they put in the parentheses. So that's all they did on that particular line. And then let me get rid of this and put it. This is really crappy. I have to type here wherever I'm at.
Do you have color coding? Can you select something in?
Yeah, do color.
But then I have to type that in color. It's a form here than color. It's not like just changing the font. I have to.
Are you in Windows?
Yeah.
Can't you just change it in Control Panel?
I
don't know.
you know what?
Later. Yeah.
Mouse cursor, mouse settings. Let's see here. I guess like.
I mean,
possibly. This is Windows 10. I don't use 10. I mean,
do you see the cursor normal size? I mean, you know, because the rest of us are seeing it small.
Okay.
Oh, you know what? I do remember in mouse you can actually hit control and it actually right here. But I don't know if the outside chat will see that. But let me see if I can make it bigger here. Pointers.
You have a selection you can use there.
Text select, resize, extra large, black.
There we go.
All right, we'll give it a shot. Does that help?
That's better, I think.
Better?
Yeah, and the control works.
Yeah.
Pushing control is not working. There you go.
Yeah, years ago, I used to have a walking dinosaur as my cursor.
But you walk the
really?
dinosaur.
Yeah, you can download cursors from the internet, and so I had it at work, and people would walk up to my computer and go, "What the fuck?" And this is my cursor. It was just a little dinosaur that walked. It's sort of a brontosaurus kind of thing.
But you know what? I'll look into it a little bit more. Maybe there's an add-on program I can get.
Yeah, look into that
until I get the little tablet thing. But okay, can the outside chat see the cursor? When I hit control, it produces this little round thing. Does that help? But I don't know if okay.
Yeah.
Okay.
Yeah.
There we go.
Awesome. So here, right here, and here, all they did was they did the same thing. They factored stuff out.
Right.
Okay. So they're factored out here. What they did is they factored out this G, this quantity, G times, the function G x plus delta x from here and here, and they just factored this out, and this is what's left over, and the f of x. So, excuse me, all they do is factoring. So, anyways, let's actually go on to the more meat and potatoes. You guys can figure out the factoring.
Yeah.
This is where you actually apply the property of limits. Now, we didn't really go over the properties of limits. I explained them at one point, right? But we didn't really go over them too much. Some of these are pretty self-explanatory. The property of limits, for example, here, the product of two functions, the limit as x approaches a, you can actually separate them. You can just say, okay, the limit of the product of these two functions is going to be equal to the limit of one function as x approaches a times the limit of the other function as x approaches a. Okay, not too difficult. You're just separating them out. Same thing with addition of subtraction. If you add these together, this will be addition. If it's subtraction, you subtract them. So the difference between two functions, the limit is equal to the limit of one function minus the limit of the other function. That's it. Really not that complicated. But these are two properties of limits. We did go over those the other day if people watched. So when they end up with this equation here, okay, what's happening is that they're just breaking this equation down by using these properties. They're saying, here I have one, we go up here, here's one term, right? One part of the function, so one part of the equation times another part of the equation. Remember, terms are technically, terms are separated by plus or minus in algebra, by the way. Okay, so all they're saying is the limit of this times this is equal to limit times this equation times the limit of this. That's it. And then they're doing the same thing here. You have a plus sign, and then you have f of x times this bracketed group here. And they're saying, okay, the limit of f of x here is times the limit of the group here. That's it. That's all they're doing. They're just breaking it down. This makes it a little more wieldable, right? This makes it a little bit easier to see what's going on than this. Would you agree, Midnight? If you just look at this, right? If you break it down into the limits and you end up with this, I think this is, even though it looks a little more complicated, it's actually a hell of a lot simpler if you think about it, right? Because now that we understand limits, right?
Yeah, because you do the derivative of the first times the limit of I get it.
Yeah. Because once you start taking the limits, you'll see exactly what's going on here.
Yeah, and then that makes sense. So you have the derivative of f times g plus. I get it. Yeah.
Okay, so what happens?
It's a little hard for me to get into.
Well, let's do the limits, right? This part right here, you would recognize this equation here as first principle, right? This is exactly the form that we would use, right? y2 minus y1 over delta x. So so delta x approaches 0, right? And here you have the same thing as delta x approaches 0 and delta x approaches 0. So what happens is these start going away, okay? And what do you end up with? If I have, like, for example, here, what's the limit of f of x as delta x goes to 0? Oh, it's just f of x. It's a constant. Delta x has nothing in here. There's no delta x in here. So this is a constant. So I'm left with this f of x.
Yeah,
and here,
the deltas just leave.
Yeah, and right here, what happens is delta x goes to 0. Well, this just goes to 0. I'm left with g of x. So here, right, this first thing right here, we recognize this as the derivative, right? This is the first principle. This is the definition of a derivative.
Yeah,
so
Steve, I don't want to get too ahead, but try proving the quotient rule.
We are doing the quotient rule, but not today.
Well, yeah, I know. I didn't mean today, but
yeah. Well, product chain rule, then I'm gonna do the quotient rule. So, anyways, so this right here is literally the definition of a derivative, f prime, right? So f prime of x. This is this equation here, by definition, times what happens in this part. And L of G, what I just told you, what goes away here?
The delta x.
The delta x, leaving me limit G of x right here. So I'm left with the derivative of prime times G of x plus. So what happens here? What am I left with?
Just the f.
F of x.
Yeah, f of x, right? Because
delta x. Now, again, think about it. It's not x goes to 0. It's delta x goes to 0. Well, delta x is not even in the argument here. It has nothing to do with it. Yeah. So it's just f of x that leaves me with. And here, this is the same thing as here, only using g as a function rather than f. So what happens here? This is the derivative of g of x, right?
Yes.
By definition. So wait a minute, 1 sec. Let me finish. Okay. 1 sec. So does this equation, right, f prime of x, the h of x, what we're trying to solve here, does that not look like the very first equation here?
Yes.
Because these are the same thing. So h of x, h prime of x. I guess I could have thrown this in here. They didn't include it, but I'll put it in here for clarification purposes. But oops, that monk's symbol. And so they just proved that h of x prime is equal to this. And again, that's exactly what we're trying to do up here. That h prime of x is equal to this.
Okay.
See where my cursor is? So this is what we're trying to prove. And we ended up with this. There you
Now,
go.
Steve,
That's the proof in the product rule for Wikipedia. Go ahead.
Okay, I was just gonna ask you, would it be a fair question to ask as to why it's done this way?
What do you mean?
Like,
why
okay, why is it an f prime of x times g plus f of x times the times?
You know what? You know what? That's a great question, actually. But I'm going to give you as a homework assignment. I want you to take two functions. Take two functions. Just like x squared. Yeah, pick anything you want. But I mean, use something with kind of exponents, because that way you kind of get the idea.
Yeah.
And just take them individually, and then sum them together, right? And then take the derivative of that and see if you get the same answer as if you do it this way. Because you won't.
The homework?
Take two derivatives. Take two functions. F of x. Let's say x squared. G of x. Take 2 of x squared. Okay.
Yep.
And again, I'm just throwing these numbers. I'm not sure if, how you would do this exactly, because I haven't done it. But and then take the multiplication of that, right? So 2 times 2x squared would be 4x squared. And then take the derivative of that, which would be 8x, right?
Yeah.
That's not going to be the same as if you do it this format. But I would have to do it in a Wolfram Alpha and just do it.
No, I know it's not the same, but
basically it doesn't work out. It doesn't work out the same, right? You're getting two different answers. So this actually gives you the correct derivative for taking the product of two functions.
Well, yes, I know. I was just wondering, like, why it's done like that and how it would look graphically.
Use Desmos and figure it out that way. The graphing program that I use, Desmos.
Yes, I know. I've used it before. Yeah. Moving on.
Yeah.
Sorry, I just figured I'd ask.
Yeah, it's well, no, it's a great question. I didn't get into that to show you kind of why you would get the problem if you didn't do it this way.
What does QED mean again?
Quod
demonstrandum.
Yeah, quad. What is it? Quod. I hate Latin.
As demonstrated.
It basically means in English it means that to which would to be demonstrated.
Quad.
Quad erat demonstrandum.
Quad estros demonstratum.
Erat.
Quad erat demonstratum.
Quad erat demonstratum.
I'm showing you guys math, not Latin. So
erat.
Yeah.
Quad erat demonstratum.
Got it.
Yay. See,
okay.
You know what it says on my wiki? Steve can learn new things.
Well, everyone can learn new things, but moving on.
But that's my wiki skill.
Yes.
I have one wiki skill. Oh, okay, so anyways, yeah, quad erat demonstratum. But it basically means that was meant to be demonstrated, or to which to be demonstrated. Okay. So actually, by the way, Midnight, in response to your question, Brian says the reason we do it this way because we want the right answer.
Okay, fair enough.
That's fair enough, right?
Whatever. Yeah. Moving on. I mean, I guess some questions have no answers, I guess.
So what we're going to do here, we're going to jump right into a little bit of trig, because we know everybody loves trig. Yeah, right. I'm going to tell you right off the bat.
Yay! Let's hear it for trig.
Oh, God.
Yay,
no.
trig. Sorry, I had to do that.
I'm going to tell you right off the bat. You will have to prove this at some point if you take trig, but just know that the derivative of sine x is equal to cosine x. Okay, just accept it as reality. This is one of those things that you'll learn in college, or you'll learn like in nuke school. They'll say, "This is true." You don't understand why it's true. You won't understand why it's true until like later on. Okay, so just accept that it's the reality, and then you could prove it later on. It's not an easy proof. It's not an easy proof. So we're going to take the function of f of x squared sine of x, and I'm going to have the assumption everybody knows what sine x actually is. Sine is a waveform, right? Save as a function.
Yes.
I am going to have a presentation eventually on sine and cosine wave functions. I think it's critical because Jade is going to be doing specifically on trig. And if somebody doesn't really know what cosine or sine is, then excuse me, it might excuse me, it might be difficult later on. So
yeah, we'll be drawing unit circles.
Yeah, she's gonna be doing the unit circle. Yeah. So, anyways,
yeah, one of my favorite things, the unit circle, because everything makes so much sense from there.
yeah.
If you know how to draw a unit circle, you know trigonometry. You can.
Yeah, I'm not
everything about trigonometry.
Whenever I would take a test, first thing I do is in the corner of the paper, I draw a unit circle.
Yep.
Yeah, Nuke School didn't really harp on that much, and I think it was one of the downfalls. I wish it would have more. But okay, so we want to find the derivative of this. Okay, so the x squared sine of x. Now, excuse me. One of the things you asked Midnight is like, what? This is a good example of your question here. What happens if I just took the derivative as you think of, well, you know, you might have suggested, right? If I just say, okay, if I just take the derivative of this, I get, well, 2x sine, cosine x, right? But that's if I just throw in if I know sine of x of derivative of that, I get cosine x, and the derivative of x squared is 2x, right? So that what you think that the answer would be if you didn't use the product rule, right? It would just be 2x cosine x. But let's see if we actually get that, okay? So, by the way, you can see that we don't, but Midnight, you pay attention? You see what I'm saying? If you just did it without using the product rule, you'd get 2x cosine x, right?
I mean, Steve, I think my question was like why it was done like that, but Brian is just like because we want the right answer, so I'm like moving on.
Well, yeah, but I want to make sure that if you don't use the product rule, if you didn't understand the product rule, you just said, oh yeah, this is just 2x cosine x, then you'd be wrong. But let me ask you this, Midnight, before you go further, right? See where my mouse is? If this was a plus in between there, if there's a binary operator of addition rather than multiplication, x squared plus sine x, could you do that derivative in your head? It's really easy.
Well, yeah, it's you know the addition property. I think you're just adding the derivatives.
Right. So what would do the derivative of x squared plus sine x?
X.
Bernie, I'm supposed to answer that.
Well, no. Well, no, it wouldn't be just x.
Well, no, it would be 2x plus cosine.
X. Yeah, 2x plus cosine x.
Yeah,
right?
2x.
So addition's easy, right? We don't have to apply any special rules like this.
No.
But, okay, so we're moving on here. So assume that the function f of x equals sine and f prime of x equals cosine x, right? Yes, RSC got it right, but RSC's smart. Yes, and you're exactly right. It would be 2x plus cosine x. So here's the
say that?
Yeah, you're right. No, I said you're exactly right. So x squared sine of x. Here's my function. Now I want to take the derivative of that, right? Using the product rule, right? Which again I didn't show again, but it looks like this, right? Remember the product rule? I want the derivative of one function times the function, another function, plus the function times the derivative of the second function. That's the form. So what I'm going to do is I'm going to use Leibniz notation on this. And the reason I use Leibniz notation on this is because I think it actually shows easier what I'm taking the derivative of.
Yeah, I'm starting to get the hang of this notation.
Just to confuse everybody.
Well,
yeah, I mean, switching notations back and forth.
Yeah, I used to get confused with this notation, but now it basically means the same thing. It's still derivative.
d over dx means f prime. Okay,
yeah,
that's it.
Okay, that's.
I like this notation because when you start doing differential equations, dx and du and dv make a lot more sense because you can actually separate them out. Do not think of this really as d divided by dx. However, this is the caveat. Even though this is not d divided by dx, it's not. Don't think of it as d over dx division. But when you get into differential equations, you can actually start separating the variables out in the differential. So dy over dx is separatable, meaning I can take the dx and move it out from the denominator, even though it's not a denominator. Don't think of this as a fraction, even though it acts as a fraction sometimes. Do you have a better way to explain that, Jade? You know what I'm saying, but does it make sense to everybody?
Yeah, for now, whenever you see d over dx or anything similar to that, it's got a d in it or a delta in it, because sometimes there's not a d, there's a delta. It's not.
Yeah. So this is do not, here we go. I know how to explain it. Do not think of this for the people that have not had math that are watching this. This is not dx squared. Well, It is dx squared over dx. This is actually true. You can actually take this x squared and you can move it up here. So it's actually dx squared over dx. But yeah, you know what? I'm going to stop there because you can actually rearrange this and actually make this into a differential.
But for now, just look at it as the way Steve said it is d over dx.
Yeah.
Not d divided by dx. It's d over dx.
Yeah.
Yes.
Now, like I said, when you do get a differentials, though, if this was like dy over dx, you could actually separate it out and go dy equals x squared dx,
right?
Which is which means with respect to x. But
let's treat it as f prime.
Yeah,
is what you're
saying.
saying.
F prime. So, anyways, I want the derivative of this x squared times this. Right. This is the function. This doesn't change. Plus this function times the derivative of this. Okay, just like in the form that's given above here. Back here, right? It's in that form. So now that I have it in the correct form for the product rule, let's actually do it. Midnight, what's the derivative of x squared?
2x.
2x. This goes, okay, so you don't need this anymore. I've taken the derivative. I've got one term, right? This term is equal to this part of the, right here, or my main thing, is equal to that part, and then we're going to be doing that second part across the addition sign. Okay, so let's do this part. I don't take the derivative of x squared, right? But I take the derivative of sine x, which I've already told you is what?
Cosine x.
Cosine x. And again, just accept it. You'll have to prove it later on. I don't want to do that proof. It's not an easy proof, but I've done it before. Okay, so my derivative is equal to 2x sine x plus x squared plus cosine x. So the derivative of this formula is equal to this, right? So again, that's different than just saying, oh, it's 2x cosine x, right? Which a lot of, I'm sure, calc students make that mistake, right? They don't realize they have to apply the product rule to it because this is a product of two different things. It's x squared times x sine x. So this is just implicit multiplication. That's all it is.
Right.
Okay,
and
we all caught up.
Do that is if you're, if you're confused by this, it just like you said, this is a product of two separate terms. You can separate them yourself when you're doing a problem. You can put a dot in between. You can put parentheses around them so that you understand as you're working the problem. You don't accidentally slip.
That is a great point, actually. You're allowed in math to, it's a little bit wieldy, right? But you're allowed to change things to make it clear, just for clarification purposes for yourself. If I want to change this and I want to change it to this, so I know that this is x squared twice times this quantity, you're allowed to do that. If I want to throw in, a multiplication symbol, you're allowed to do that.
Yes.
Okay. So don't think that you're not allowed to.
I would use a big dot there because that's that's you want to use this. But the problem with dot is I'm used to.
Dang it. It's actually C dot in this particular program. C dot. There you go. The problem with this is that this dot again means different things for different people. It means dot product or whatever. Right. But you'll see this dot a lot for multiplication. So you can change these things in there. Do it. Go for it. You can't change it. So
you could even, if you found it confusing, you could even put parentheses around the x squared as well.
Yes. Yeah, as long as you're not changing the order of operations, you can use grouping.
Right.
Yes.
So right here, looking at this, I could put parentheses around the x squared, and then put another parentheses around the sine x.
Yeah. Matter of fact, Super says it was mandated in his class to do it that way. I think it's a little wieldy to do it that way, but it does help learn. If I just want to say, okay, I want to isolate these
right.
things. Okay, let's do it.
It works for some people who have difficulty understanding that these are separate, and I've taught people how to do this before because it makes it so much easier for them to visualize. It depends on what works for you.
And if you're doing you're doing it in crayon, you can write it out in different colors.
Right. Yes. And so there, what Steve just did right there. See how he separated them? And you can put the dot.
See, I added this.
You don't need the dot. You could put the X or the asterisk, whatever works for you, to show you how separate those two terms are. And sometimes when you're first learning this, because this is the way I would teach people, I would show people how to do this first, it a while, they didn't need all the extra parentheses and stuff. They knew what was going on.
Yeah, but that's only when you get acquainted with it enough. It's the same principle in programming.
Exactly.
Like,
Right.
I
would write it
as
like
clearly and understandably as possible while you're learning.
Right.
The way I would write it like this. So your instructor, whatever, they're seeing that you're not changing anything, and you're just saying it is equal to this.
Exactly.
That's how I would write it.
Yeah.
But again, we were able to do this in our head because we've been exposed to this before, right?
Right.
So actually, I never knew what calculus was last week. I just Googled it. So whatever, So
let me Google that for you.
Yeah, just, if you don't know anything, just Google it. You'll be an instant. You'll be able to do the stuff in your head.
Right, exactly.
Right. So
if you don't know how to Google, there's a great site called Let Me Google That For You.
Let me Google that for you.
Yeah, you just write in what you want.
Let me Google you.
And it opens up Google and types in what you told it to search for, and then.
You know what? I'll Google you. I'll Google you. I'll Google you until you say Yahoo. Okay. All right. So let's do a special case. Okay. The only reason I added this is because I think it's an interesting special case that you will use later on, right? And that's the only reason I included this particular thing. So what is this saying here? This is called the constant multiplier rule. Do you remember this notation, Midnight? What is it saying?
No. F. No. C.
Yeah.
C. No. Sorry, I don't remember those. I don't remember the symbols.
Okay. The middle one means element of.
Element of.
And R means nope.
No.
Set of real numbers.
Real numbers.
Set of real numbers.
So this means a constant as an element of real numbers, or in other words, a C is a real number is what it's basically saying.
Yeah.
And you might see that. Now, Steve's got a nice fancy R there. But sometimes you will just see that. Right. Sometimes you will just see that as a great big R.
Right.
Yeah.
Yeah.
And that's called typesetting, by the way. That's a difference in typesetting, not notation.
Okay. C element of real numbers. Okay. And
just remember the E.
Yeah.
It sort of looks,
it's a weird.
Look at E.
Yeah, it's a weird E.
Okay.
That's exactly right.
All right. So C is an element of real numbers. C is a real number, and f of x is differentiatable. So the function is able to be differentiated. Then a constant times the function is also differentiatable, and its derivative C times the product, which means the product of C times f prime of x. What this is saying, this is really actually a fancy way of saying this. Look, if I have C times some function, and I take the derivative, and the derivative of the function times C is going to be it's going to be equal to the function, the derivative of the function times the constant plus the derivative of the constant plus the function. And all that is a special case of this. Okay, that's the same thing, only with a C instead, where C is a constant. Now, if that's a special case, right, what happens in this part of the equation? What happens to the derivative of C times F? What's the derivative of any constant? Yeah, the derivative of any constant is 0, right? We've learned that before in one of my prior things. So 0 times F just goes away. So what am I left with, Midnight?
You're left with constant times C times the derivative of F.
Exactly.
Right.
So I mean, all this is saying is that I'm left with a C times the derivative of F. Okay. So let's actually go through it. Let's actually see if it works. Here's my example: f x squared. I use x squared a lot, by the way, because it's a very simple function, right?
Yeah.
So if it works for a simple function, you can kind of see how to it's used for other functions. So we have a constant that C equals 2. 2 is a real number, right? So it satisfies the condition of here. CL is an element of real numbers. So I have a constant times a function. So I just stick in 2 times the function. I have it's 2x, right? Right, we're good so far. And I take the derivative of 2x squared, right? And by the way, you could do this in your head. Before I even get to this right here, what's the derivative of 2x squared?
4x.
4x, right? We can do that in our head nowadays, by the way, which I kind of funny that people claim to be an engineer can't do that in their head, right? When I ask simple questions like this, it's not sharpshooting. It's not asking.
Well, no. Actually, I've asked him once. He gave me the right answer, but then I asked him to find the derivative of ex. He's like, I don't know.
EX.
I'm like, what?
Yeah, the derivative of e to the x is e to the x, which I proved the other day, right? A couple weeks ago. But anyways, so here we have a situation, since we already know the derivative of dx 2x squared, right, is 4x, which would just be this right here, right? C times a derivative. So I want to prove this right. I just say 2 times the constant of f of the derivative of x squared. So the derivative of 2 times the derivative of x squared, this would be the constant times the derivative of x squared is equal to 2 times 2x equals 4x.
Yeah.
Let me phrase that very carefully, because you can't just take the derivative of 2 times the derivative of x squared, because then you get 0. So you're applying the product rule, which is here. I'm left with 4x. So it's the same thing. And let me ask you, why do you think that's kind of useful? It's useful because you can draw things out. If somebody says, look, I'm giving you d over dx 3x cubed, right? I know, because if I take the derivative of all this using the product rule, I'm going to be left with 9x squared. I can do that in my head as well. I could do the same thing by just taking the 3 out. I can draw it across this d over dx, and I'm left with 3 times d over dx. Well, what's the derivative of x cubed?
3x squared.
3x squared. And then what's 3x squared times 3?
9x squared.
9x squared. Either way I do it, I get the same answer, right? That's the special case. That's why it's handy to know, because I could either say I could just take this derivative, and instead of applying the power rule, right, which you want to show the steps, which is going to be a little bit more wieldy, right? You'd have to go back and do it this method. No, I could just say, oh, look, I'm just drawing the 3 out. I'm just taking the derivative of x cubed, giving me 3x squared, and then I'm times it by the constant, right? Give me 9x squared. Either way you do it, you come up the same way. So that's a special case. Special cases are great.
Next, the chain rule, which I finally figured out how to do a little bit, I guess.
Yeah.
Okay, I'm going to ask you guys, you want to continue the chain rule, or you guys burned out? Because the chain rule is going to take more than one session, I think. This is just...
but I'm tired.
Yeah,
but
we can always do the chain rule next time.
Yeah.
You guys want to do the chain rule next time, because that kind of is in a class by itself, because it gets into some pretty complicated stuff that I mean, look how complicated this gets pretty quickly. I think it's deserving of its own hangout.
Yeah,
so we're going to call this.
Yeah.
And then we'll get
by
into
the way,
part
the fact that the derivative of a constant is 0 comes in very, very handy sometimes, because you can manipulate your equations to get rid of those.
Yes.
Yeah. And Steve knows exactly what I'm talking about. Yeah.
The hardest thing in math that I found was knowing what to do to rearrange the equation in order for you to go further to do something.
Right.
Okay? Because the concepts are great, but it's really difficult to manipulate formulas sometimes. Go ahead. Sorry.
I was just going to say, I have just for those who are listening and somebody who might want to have some fun. I have a problem that really simple, but takes some figuring and manipulation. The math of it is really simple, because you're going to be taking a derivative. The equation is the interesting part. So I'm just going to give this to you for those who want to try it. What is the largest rectangle that you can fit in a triangle?
Oh, I hate inscribing stuff.
Well, wait, hold on. How big is a triangle?
It doesn't make any difference. It doesn't make any difference. See, what you have to do is you have to put all your variables in there. You put the rectangle, the shape of the rectangle, the 4 sides of the rectangle.
Yeah, no, I can see it in my head. You're inscribing the rectangle in the triangle, right?
Rectangle inside a triangle,
right.
And then you have to put the 4 sides of the rectangle in terms of the triangle, because you know what the triangle is.
That also gives you 3 additional triangles.
Right. So you've got a triangle, right? And the triangle has 3 vertices, A, B, and C, 3 angles, alpha, beta, and gamma, right? And then it also has the height, H. Well, actually, it has 3 heights, H1, H2, and it has different heights.
Well, you know what? Why don't you do that proof in a hangout or something?
Okay, well, I'll just put it out there for people. You know what? I'll make a post about it.
Yeah.
And then we can go into a hangout
Do it.
and try and do it. Because for those of you who don't know, whenever you're doing a max or a min problem, you're looking for the maximum or the minimum of something, you're taking a derivative.
Yeah, and those are called constraint problems.
Right. And the derivative is actually very simple, but setting the problem up is the fun part to me.
Yeah, I don't enjoy those, but
I do.
We've all had to do them.
Can I ask a question?
Yeah, sure.
Like how you just I think it was Steve who said that if you take a triangle and you put you inscribe a square, you get 3 separate triangles. Well, wouldn't you get 2 separate triangles if you're using a right angle triangle? Do I need to find a way to rephrase the question?
Yeah, I'm looking at an equilateral triangle in my head, and then visualizing the rectangular there. I don't know. It's geometry. We'll have to. I honestly,
Well, no. I mean, I asked because because I'm trying to think in my head. A right angle.
There we go. I lost you guys. For a minute. Okay. The best thing to do. Let me give you a hint. Is to assume.
Yeah, in a right triangle, you have 2 triangles. Yeah, I can see them.
Yeah, the best thing to do is to assume that you have a scalene triangle. In other words, none of the sides are equal, and it's not a right triangle. Okay? Because you're
by the way, we'll have to hang on those types of triangles one of these days for hog tie.
Yeah, because your formula, if
he doesn't think triangles exist.
If you can do it with a scalene triangle, with it's not a right triangle, right? So the 3 legs of the triangle are no 2 of them are equal, and and none of the angles are equal as well. So you've got which is a scalene triangle, and it's not a right triangle. So assume that. So if you've got the 3 vertices A, B, and C, B will be different from A to C, and those 2 will be different from B to C. You got that maybe in your head?
Yeah, I could do basic geometry, but I suck at geometry. But I could explain basic stuff. But
this is actually very simple geometry.
Yeah.
She says.
Yeah.
No, it really is. It really is, and that's kind of the trick here. The trick is thinking of how to set up the problem, because in math, one of the reasons I like this example in math, as Steve was saying, the trick is to setting up the equation.
Physics is the same way.
Right, because there are I did a ton of max-min problems in calculus.
Yeah, I haven't really been in geometry in a very long time, right? And so I wouldn't want to
max-min problems are certainly, but max-min problems certainly aren't just geometry. Max-min problems are everything.
You need to take derivatives, of course. Yeah,
but it's taking the derivative is usually the easiest part.
Well, but here's the thing: the Jade. Remember, I mentioned something about the ball bearing and taking measurements. Those are a max-min problem because you're taking the minimum error measurements to the range of the minimum error measurement to the highest range of the error measurement, and how it propagates error propagation to extrapolate and to find out what the volume is. So a small change in measurement can lead to a bigger change after derivative, because you actually take the derivative of the volume formula in order to do that. So yeah, you're exactly right.
Yeah, but it's not the taking the derivative part that's difficult. It's the setting the equation up properly that's difficult. That's where the trick comes in, and that's why I kind of like this example, because it's so general. It works the brain in terms of setting up the equation. So I'll put that out there. I'll even do a little drawing.
You do that one, and I'll actually do a little one on the ball bearing one, because I've actually had to do that one. That one actually was something we learned in the military. The nuke school, you had to. This is why we learned calc in the Navy, because they want you to understand error propagation and differentials.
Right. And what kind of micrometer did you use? Did you have a dial on your micrometer or not?
They were. I used different types actually. There was actually I had internal micrometers for if you like measuring the internal diameter of a pipe, and then you have external micrometers, calipers.
Well, there's calipers in a micrometer.
They're that type. But you know how a caliper goes on the outside? A dial micrometer will go on the outside, and then you have what you can do is you can take internal calipers if you don't have the right kind of micrometer.
Yeah, I know what those are. I was a machinist.
Oh yeah, so yeah, well, yeah, exactly. You know what? I was a machinist man in the Navy, so when you say machinist,
So
I'm
there.
like, yes.
Yeah,
But
you know what I mean? A caliper.
Oh yeah,
the,
of course.
the regular caliper that has the C on it. It looks sort of like a C with a.
We had all, yeah, we had all
you
different
had
kinds.
all
obviously.
kinds. I'm
Yeah,
sure.
I mean,
sure.
What,
But,
what part of the preventive maintenance thing for your PMS? What's it called? The preventative scheduling.
Yeah.
You had to determine if it was safe to put a certain amount of pressure in a pipe, right? People, this is why you went to nuke school, by the way. You had to know the theory because anybody can push a button and turn a valve, but you actually have to fix stuff. You have to actually know the concepts because who's going to fix this stuff? So you would have to determine whether a pipe was safe or not. And you have a minimum thickness, wall thickness based upon what's called the schedule. And the way you would determine that is you'd use like an internal caliper and then external caliper.
Right.
That'd give you a, you know, the thickness of the wall. And then you would use calculus and stuff like that to determine the you know, the minimum maximum. So there's a reason for why they do teach you this stuff in nuke school.
Yeah.
Oh yeah.
It is it's called theory to practice.
Yeah, but back when I was doing it, dial calipers were actually not as common, and dial micrometers were even less common. You know, so you actually had to read the lines.
But today I think that would introduce more of a error propagation.
It does introduce more of an error propagation, which is why for our really sensitive stuff we used an optical comparator.
How much were those?
Expensive. There was like one per department.
Oh.
And you had
I've used the dial. I've never used an optical comparator. I've used the dial type. I've used the C type of micrometer where you have that the little thing goes in and out.
Oh man, I can use those one-handed so fast. I still can.
That was actually a very common way. For example, when you would use, if I wanted to take the volume of a ball bearing, right, or something like that, you would use that type.
Yes,
right?
That's the easiest.
And the reason why you take that, you know, why you use that type though, it was preferred over just think of a simple caliper, right?
Yeah.
That only gives you a point on one point of contact with the ball bearing, but the type of you're talking about, that C clamp type. The surface area is a little bit greater. It gives you a little bit more. It's not, again, it's not that great. It still has a small point of contact, but the point of contact is generally a little bit larger than just a small point. But again, that's so fine that unless you're doing with fine tuning measurements, who cares, right?
Yeah. See, we were making don't you just love it when the mind goes blank?
And by the way, you use that for more to just spherical objects too. You use it for square type objects as well. And that's why I'm talking about you have more surface area on those type for point of contact. But
I was just going to tell you what we made, and my mind just decided to hide it. But basically, you know, like you have a plug, right?
Yeah.
Like a really complex plug, and you have the little metal parts in the plug that connect connectors. It was a connector company, so we made these connectors, and some of them were very small. So you would have to measure the connector. And what you're talking about, like, I take a micrometer in one hand, and I take the part in another hand, and the part would be just a few centimeters long. And you check it, and then you turn it, and then you check it, and then you turn it, and then you check it, and then you turn it.
Yeah, you're taking x-axis, y-axis, z-axis. You're taking different measurements across different axes, so you get an average. Right.
So you
you check it if they want a specific measurement for each axis. Sure.
Right. So you make sure it's within tolerance. Within tolerance. So that none of those were and we dealt with plus or minus hundreds usually. If we were dealing with plus or minus thousands, that's when we went to the
that's what I was saying before. The micrometer is generally 0.01, but some of the more sensitive ones are 0.001, which would be in the thousands.
Right. Yeah. It depended on what kind of parts we were using. If we used the actual contacts themselves had to be really, really close. They had to be within hundreds at least, or thousands. If we're dealing with something like the outside of the plug.
If you start talking about interferometers, I'm leaving.
Interferometers, but you know what?
Okay,
I gotta end this. But you know what? This goes to what's the difference between theory and practice, right? Obviously, Jade and myself, we've done this in practice, right? So the theory is actually applied in real world applications,
right?
And this is why the people that always have saying, "Oh, well, the Great Debate Community or Steve's channel, or whatever," they never talk about actual science, or they never educate, or they don't have any experience, or they don't know anything. You know, it's just like we have to have the experience. Okay. I mean, I can tell you right now, Jay knows about machinery, you know, machinist stuff, because clearly she knows what she's talking about because she's done this, right? I've worked like commoners too. So yeah. I just think it's funny. I still get a kick out of it. I always get a kick out of it because it's like, for God's sake, you know, you can't just learn stuff by reading Wikipedia. Yeah, it helps. Don't get me wrong, but you can't do it. You're not going to be a Wikipedian expert. But anyways, guys, let's end this because we've gone long. Yeah. We'll get in the chain rule tomorrow at some point, maybe. But again, tomorrow we also have a debate with King Crocoduck and Wayne Fillmore, so it might be postponed for other things. That's going to be at 12:30 tomorrow.
Wait, hold on. 12:30 your time?
Yeah, Pacific.
So 3:30.
3:30 Eastern.
Yeah. Yes. Okay. Ooh.
Yeah.
Which channel, here or yours?
No, mine.
Okay, sorry, Jade. Go ahead.
No, that's okay. Yeah. I said I'd probably be outside for that during that one, depending on the weather.
And then, of course, we have to have an after show. So, I mean, the chain rule might have to wait till like Monday because I got the Sunday show on Sunday or Sunday night, or you know what, maybe Saturday night. I don't know. We'll see. But it's good. But yeah, I want the chain rule to be at a separate hangout because it really is the most important formula or whatever in calculus, I think.
Important rule, yes.
Yeah, it's really, really critical. If you don't get down the chain rule, you're just going to be SOL.
Right.
So anyways, guys, RIC, Midnight, Jade, Barney, who else we got? Calzer, Charles, everybody in the live chat. Thanks for watching, guys. And I hope you guys, remembered something. This is a good review. If you've never been exposed to this before, go run with it. So if you ever do one of these classes, you're going to have a leg up. So with that, guys,